Hello everyone. In this lecture we are going to discuss about the root locus. In the first part we will see what is the root locus. Okay, so the definition of the root locus will be provided together with some examples. If you look at our standard closed loop system that we are using throughout this course, and it's shown over here, our aim in designing the controller would be our main aim, and our aim in designing the controllers would be to achieve stability for our closed loop system and also satisfy some transient specifications such as the overshoot or settling time or rise time and so on and so forth. As the simplest kind of the controller, we will keep in mind the proportional controller, which will be simply a gain. Okay, so KP will be our controller, or GC of S will be in the form of KP, a proportional controller. So for now we assume that we can satisfy the requirements using a proportional controller, but later on we will see what happens if we are not able to do so. So when we decide to use the proportional controller, we need to determine a proper value for Kp. Should Kp be equal to 10 or 25 or 3.7 or whatever value? We need to find out the proper value for Kp, which gives us the proper behavior in terms of the stability and transient specifications. Okay, so we will study, indeed we will find out the transfer function for T of S, and over there we will find out the location of the poles of T of S as a function of Kp. So we will see that as Kp changes, let's say from 0 to plus infinity or from minus infinity to 0, the location of the poles of T of S will change, will vary. This is indeed something that we already have seen, and then we will draw, we will specify how this change happens. Okay. When we know the location of the poles of the closed loop system, we will have a complete information in terms of the closed loop stability. We will know whether the closed loop system is stable or not, or how stable it is, and we will have some approximate information on step response parameters if we can approximate the whole system as a second order system. Okay, so let's see how we are going to do this. Okay, so first we assume that GP is given in the events form. GP is our process. It is given in this form, in the form of K prime times GP prime, where GP prime is in the form of a numerator over a denominator, in which the numerator is in the form of multiple zeros, let's say terms which include multiple zeros in the form of S plus Z1, S plus Z2, S plus Z3, and so on and so forth up to Z plus S plus Zm. So we have m number of zeros, and D is in the form of S plus P1 times S plus P2 times S plus Pn. So we have n number of poles. Okay, so K prime is taken out in this form. And we also assume that n and d are co-prime polynomials, so there are no zero pole cancellations. Then we define L of S as Kp, this is the lowercase letter k, Kp times Gp of S. because our GC, the controller that we are going to use, is a proportional gain. So this will be indeed equal to Kp times capital K prime times n over d. And then we define Kp times K prime as a new variable, and we call it rho. Okay, so this will be equal to rho times n over d. So this is quite important. We will consider L in the form of rho times n over d. And afterwards, we can find out the transfer function for T of S. L over 1 plus L. If we replace L with rho times n over d, we will get T of S in the form of rho times n over d plus rho times n of S. So that's how we get the closed loop transfer function. And obviously, if we want to find out the location of the poles of the closed loop system, we need to set the denominator to 0. So d plus rho times n equal to 0 will determine the location of the closed loop poles of the system. And over here, you can see that the location of the closed loop poles of the system will change as the value of rho changes. And rho is indeed, if we assume that K prime is constant, rho will change as Kp changes. Okay? In some cases, K prime will be equal to 1 indeed, and then rho will be equal to Kp. But that's not something important. So this is quite important to remember. D plus rho times n equal to 0 determines the location of the closed loop poles of the system. Then the root locus of a feedback system will be a plot of the poles of the closed loop system as a parameter, which is rho in this case, in R changes. So rho will go from minus infinity to 0 and then to plus infinity. It will change over R, okay, over all the real numbers. And then we will draw the location of the closed loop poles of the system, and this will give us the root locus. We will see later how useful this root locus will be in terms of designing a controller. Over here, we have a simple example. A camera system is provided over here. We have the transfer function for the motor and camera in the form of K2 over S times S plus 10. Okay, so this is the transfer function that we have for the camera. And then an amplifier is used as a controller. And we have the unit negative feedback, okay? The gain for the amplifier is indeed considered as K1. Now, for this system, we can find out the closed loop transfer function. It is quite simple. It will be in the form of K over S squared plus 10S plus K, where K is equal to K1 times K2. You just need to apply the feedback rule that you know. Now, we can assume that K2, which is for the camera and motor, is constant, and then as K1 changes, the value of K will change. To find out the poles of the closed loop system, we set D plus K times N equal to 0, which is S squared plus 10S plus K equal to 0, the denominator of the closed loop system. So for this second order polynomial, it's quite easy to find out the value of the roots, let's say, of the polynomial as a function of rho, which is equal to K for positive values. We will call it as the positive locus, and you can see it over here. If we set, let me maybe show you a few values. If we set k equal to 0, we will get s squared plus 10s equal to 0. This will give us two poles, s1 at 0 and s2 at minus 10. So initially we start from here and here. Okay, and you can see that k is equal to 0 over there. Then if we increase the value of k to 5, 15, 25, let's say. Let me write down what we get for k equal to 25. When k is equal to 25, we will have s squared plus 10s plus 25 equal to 0. And then s1 and s2 both will be at minus 5. So we'll have two poles over here, repeated poles. And then if we increase the value of k further, the roots will become complex. You can see that as the value of k increases to 30, 35, 40, 45, and 50, the closed poles also change their locations. If we change the value of k very gradually, let's say, and then connect the location of the poles that we get to each other through a line, we will get the positive locus curve or the Root-Locus curve. And if we do so, we will get this. So for one pole, it will start from 0. It will move towards minus 5 on the real axis, and then it will go towards some complex values. And for the other one, it will start from minus 10. It will move towards minus 5 as well. And then it will move towards complex values downwards. This is what we get for the positive values of k or rho. We call it positive locus. For the negative values, we'll get the negative locus curve. We will see how to get the negative locus curve in the upcoming examples. But for now, keep in mind that we will have two parts for our Root-Locus, the positive locus and the negative locus. In the next video, we will go through the phase and magnitude conditions, which are the, let's say, quite essential rules that you need to know when dealing with the Root-Locus approach.